Michael Monroe. I'm a technical products specialist for Elma Electronic. I've been working with VPX since before the beginning, since more and more since 2006. And I want to talk a little bit today, explain why VPX has become the platform of choice for our industry. There's a lot of different factors that go into this, and many of them are going to be familiar to you from the presentations you've heard already, but I want to try and bring them all together. So just to give a little background, ATCA was one of the early serial architectures that came out. There was really PICMIC 216 before that. VDA46 as a concept was first presented at a VSO meeting in 2003 by Stuart Doerr of Die4. VDA46 became a standard in 2007. Then in 2010, VDA65 was released. So today, VPX is really 10 years old, or by the end of this year, VPX as a release standard will be 10 years old. What was happening at the time it was developed, there were standards, serial standards, and many of you might remember Ray Alderman's lists of serial fabrics. It got up to around 62, and that was in 2004. You can see I just put some notes down there to show a little bit about the progression of other architectures, including the PCI Express that was developed to around a serial point-to-point architecture. So what was the driving reason for serial architectures? The driving reason was speed. Multidrop buses were never going to be able to achieve that speed because of bus loading and other complexities of the design. So today we're looking at standards that have been released up to 25 gigabits per lane. There's several people have mentioned the 100G based KR4, and that sits ahead of us, and it's going to be easy at some point, I think, to compute. You won't be able to talk about KR channels anymore because there's 10G based KR10, and there's already 25G based KR as well. VDA65 introduced the idea of different developmental backplane topologies. VDA46 had given us one backplane topology, a full mesh. In 2010, VDA65 offered us 10. That should have been 2012. It was up to 37 with the release that was just balloted this week of VDA65.1. There's now 51 different developmental backplane topologies. So there's all kinds of meshes or combinations of meshes and other connections within them. There's also a whole series of different types of central switched topologies. And what I tell companies when we're talking to them is with all of these different developmental backplanes, the one thing I can tell you is that the one you need for your application is not there. But the good news is that you'll be able to prototype, and you'll be able to do early development because we've learned a lot of ways to join together existing backplane designs together with single slot and cables, and that will help you get through so you don't have to develop a custom backplane just to develop your proposed system. You can usually avoid that towards the end of the project. So there's all those backplane topologies and the number of slot profiles. VPX backplanes are defined as a basis of slot profiles and how they're interconnected together. And the slot profiles have been growing rapidly. Today we've got 81 slot profiles. That's a combination of 3 and 6U slot profiles. So that's a wealth to choose from to put together your designs. And every design will have custom aspects to it, but the way in which backplanes have been defined within VDA65.1 provides a template that if you describe your custom backplane in accordance with this template, using as many of the building blocks as possible, it's going to be very easy for your vendor to interpret what you want and respond to you more quickly. And so that's one of the other advantages of a COT system, even when the end result is often a very customized solution. What makes it the system of choice today is that there's a really vibrant ecosystem with many companies offering VPX boards. And I know I've I know a couple that I've left off of this list, but just to give you an idea, there's approaching 35 different suppliers who are offering COTS boards. And that means that whatever your application is, there are people out there interested in talking to you about it. There's also a lot of other building blocks available. There's mezzanine cards that have been used for years now. The XMC products all allow you to add additional capabilities to a VPX card, whether it's a 3U card or a 6U card. There's now a growing family of FMC cards. You saw Interface Concepts showed you a FMC card with 2 reflex photonics optical engines on it. FMC Plus is being developed to support faster communication to the main board to keep up with the fastest Xilinx processors. So Xilinx is an important partner on the FMC Plus effort. But that adds to the richness of the VPX architecture. There's also plug-in power supplies. If you're doing things in a lab system, it's undoubtedly cheaper to use a frame-mounted power supply that's buried somewhere in the back of the enclosure. But if you're deploying a system in a small amount of space, like an ATR enclosure, you'll want plug-in power supplies that can be serviced, removed easily, and there's a growing number of plug-in power supplies to choose from. There's also already 2 suppliers of VITA 46.11 compliant shelf managers. This is going to be a growing area of interest, and we'll touch on this a little bit later. But that is an important development within VPX. We've been talking a lot about optical and RF, but the shelf management, I think, in the future is going to be viewed as extremely important as well. So there's other areas of standardization that adds to the value of VPX. VITA 49 has been going on for a number of years now, and this allows for software-defined radios that are built to a common standard, which means they can plug into a system. I'm going to talk also, I'll mention the CERTIC backplane in a few slides, and that's a backplane designed to accept multiple software-defined radios for all different types of applications of electronic warfare and radars. And so this allows, instead of having a separate box for every piece of equipment within a vehicle, now you can have one chassis. Those vehicles can, different components can share the same power supply. They can share the same monitor, the same management software. The Victory architecture provides, for a standard interface and defines system software that is acceptable. And that's also being applied now to VPX. NavAir is in the beginning of the host architecture. I think we're going to hear later tomorrow about the host architecture. But this is one, as much as we tried to build in interoperability to VITA 65, and that was why it's called OpenVPX, it's hard to build one system that will accept multiple single board computers. And the host effort is, and the same will be very true for shelf management, to manage the different modules within a system. So the host architecture is going to create another level of standardization. There's a study group within VITA, but the Navy, I think wisely, wants to control the host architecture, because one thing that it's hard to get this group to do is we'll add new features, but we don't want to take away features, because we all have vested interests. We've all built things certain ways, and we're willing to consider new ways to do it, but we don't want to have to give up our old ways. Host is going to define things in a way that it suits the end customer, and they don't want it to be subject to debate. They'll take input from the VSO, but they want to be in ultimate control of their document, and because they're a large user, we'll all be happy to follow along. The connectors are always an important part of any type of backplane architecture, and there's a whole series of modules that you've been seeing today to support RF directly through the backplane, so it doesn't have to come off the front panel. Here's a couple examples. You can see the 3-row version of VITA 67.3. You can see the existing 2-row, 8-cavity version that can be used. It was developed, mainly with 6U in mind, but it's already been used in 3U applications. These are an example on the left side of the screen of the type of cabling. If you're using flexible cabling, we've also done ones with semi-rigid cabling that has to be formed. At the same time, I wanted to also mention radial clocks. This is also one of the newest developments within VPX, and radial clocks allow a new level of instrumentation or opens up instrumentation-like applications, ones where there's a lot of A to D conversion, and you need to have multiple boards with common strobes, and you might need pairs of boards that are being triggered at different speeds. So with a central radial clock, you can drive actually both the ref clock and the aux clock separately to each card, the pairs of cards. A lot of flexibility there. Optical is really just beginning, but there are some existing applications. We've been selling a lot of we designed the 3U optical backplane for a group at Johns Hopkins, and it was being used together with the Pentec board. And we know, anyway, so we've been now getting requests for this backplane in many other parts of the country for the other applications. It was the one passed around when you saw here today. There are several suppliers who are really focusing on our market with optical transceivers. I have in there a picture I took of an MT ferrule with 64 fibers in it. It's one that is a columnated beam, so you don't have to have tight, intimate contact. You might be aware, if you've been involved in optics in other industries, that you can get an MT ferrule with 5 rows and 75 to support 70 fibers. But what you don't realize often is that takes a lot of force to close it. It was felt within the Eurocard mechanical structure that really 24 fibers was the most that we could get enough pressure to securely intermate. But if we have a system where they don't actually, the ends of the fibers don't have to touch, then we can, a lot of things work better. We don't have the mechanical stress on the ferrule itself. So now instead of having 12 in a row, we can fit 16 in a row. We can have 4 rows of them, and 64 fibers, I think, is an amazing number to have on a single 3U card, because now you think about the size of the devices just to drive that many, but it'll make an optical switch, I think, a real practicality. This isn't the most complicated, most complex VPX backplane we've developed, but it is the most complex VPX backplane we've developed that we can talk about. So I think this is a really valuable thing to have. This backplane is one of 2 similar backplanes that will be in VITA 65.1. This is the 15.3.6 timing backplane. It has all the features listed down on the side, but you can see the connectors themselves. You see a 12-cavity RF connector. You see these combo connectors that have been pointed out in Mike Walmsley's presentation with 4 RF modules and an optical module. There's the 3-row one that's used for the timing card. By the way, the same timing card's used in the Navy program. A backplane was developed by Annapolis Microsystems with Johns Hopkins leading the design on that system, but it uses the same card, so there's a lot of commonality. This is an interesting area in that all 3 services are following this work and are closely coordinating their efforts. They've had liaisons. Greg has served as liaison between the Army and the Navy effort. Patrick Collier worked for the Air Force and now is working for the Navy. So there's really, it's a small group, but across all the services, and I think that adds even further value that could never have been predicted to exist with something like VPX. What you don't see, so I've got a view from the front above and a view from the back, but what you don't see is what all the cabling looks like that. It's a complicated cabling system with cables going from slot to slot, other cables going from individual slots out to connectors on the surface. There's connectors there that you don't often see for supporting maintenance ports on different slots. And it really now, because of the effort around this and because this same architecture is serving as a basis for what Host is doing in the Navy, or similar architecture is being used, we're getting requests for variations of this backplane from many other players that we didn't know were involved or interested. This gives you an idea of the topology diagram. This is a lot more complicated than many of the topology diagrams within VITA 65.1. You can see the gray squares at the top of some of the slots represent the VITA 66 and VITA 67 connectors. There's actually two groups of expansion planes. Those are the dark purple ones. The yellow, the data plane, is divided into two separate data planes with some of the switch cards supporting both data planes with isolation between the two. There's a control plane as well as you would expect, and then you can see the radial clocks. In addition to the radial clocks emanating from slot 7 in this diagram, there are also the two of the boards in each group of those boards connected with the expansion plane. There's also a separate clock 1 and reset, so that those boards can work together more effectively. And notice that you won't see, actually, I modified the drawing that's in the VITA 65.1 to show there's two plug-in power supplies. So although we call it a 12-slot central switched architecture, it's really a 14-slot backplane. So this just gives you an idea of the slot profiles, what they look like in each slot. So you can see their pairs. I've just tried to arrange them as they're arranged in the actual backplane. You can find all of these slot profiles. The numbers, the nomenclature for slot profiles can be confusing because it describes the features of them, but really the features can be, you can have the same number of pipes but have them arranged a little differently. So the 3 digits at the end, if it's a 14.4.1, that's really the unique chapter that describes that particular slot profile. And I should say, of all the backplane profiles, slot profiles, and module profiles, if you look at those last 3 digits in their descriptor, that will take you always to a specific chapter within VITA 65 where it's the product is described. And then there are often different dash numbers associated with it, and I think Greg will get into that tomorrow to talk about the VITA 65.1. And I think that's just about the last slide. This just summarizes all those aspects that I think that together are the fixings in this cauldron of VPX features that makes this really the platform of choice, not just for today, but I think pretty far into the future. Thank you.